Yeah, well, hello and welcome to everyone. So we are the Astrobiology Society here at the University of Manchester, and this is our Frontiers Award, a congress that aims to acknowledge creativity and critical and further thinking, especially for astrobiologists, but we encourage even non-astrobiologists to join. So I'm here today, among with other people, with the rest of the Society Committee. I'm Luke, Mark, and Sylvia. If you want to say hello to the people.
And I'm Luke, and I'm the Community and Outreach Coordinator.
Yep. Welcome everyone, and I'm Joaquin. I'm the president of the society. So as you may be aware, this is going to work. This is our brief introduction, and then we will let our jury to say a few words at the beginning, and then our speakers will carry on. We have today 11 presentations on very exciting topics, from the origin of life, evolution, complex life, ET civilizations, all kind of stuff, and very nice topics. So they will be the main characters today. So even if you are a bit ahead of schedule, maybe it's time for our jury to introduce themselves. So they are Michael Garrett, director of the George Bank Center, Matthew Cobb, professor of zoology at the University of Manchester, and Rima Colley, research fellow in HSTM at the University of Manchester as well. So welcome to the three of you.
Thank you.
So, well, they are, as you know, they are the teaching staff for the RBL unit from the UCIL section here at the University of Manchester. And well, if you want to say anything to our speakers and to our attendees.
Are you asking us to say a few words? I'm sorry, I never.
Yeah, sure.
No, I just congratulations to all four of you setting this up. It looks really an exciting couple of hours that we have in front of us, the Frontier Awards. I think it's a great initiative. So congratulations to you and to all the society members for bringing this all together. I think the thing about this field that's really interesting is that there's always something new. So not quite every day, but almost every week, there's something really to get excited about. So this week we had the Ingenuity helicopter, which is clearly it will allow us to be able to explore Mars in a completely different way than we've ever done it before. And so I think for astrobiology, that will be, a very important step forward. But the other thing that's interesting, and it's also reflected in your program, is this very much this multidisciplinary aspect to the topic. I always like to say this is an area where everyone can make a contribution to it. It really doesn't matter which fields that you're in. There's something to contribute to this huge topic, and that's what we try to bring from the Are We Alone course that we run from USO, the University College for Interdisciplinary Learning, where obviously there's a focus on sort of astronomy, astrophysics, biology, astrobiology, but we also have Ray there looking at the sort of cultural and societal aspects of some of the questions that these kind of areas can also sort of raise. So I know that some of you have taken that course in the past. If you haven't taken the course, then let me encourage you to go to the USO website and look us up. It's really the first semester of each year. It's open to anyone in the faculty. And I think if you're interested in the Astrobiology Society, you'll also be interested in that course. So I think all I'd like to say is to wish all the presenters all the very best of luck. We're very much looking forward to listening to the presentations, and then I believe the committee will give us a subset of presentations to rank. Yeah, all the very best to everyone today, and very much looking forward to the next few hours. Thanks.
Yeah, that's so kind of you. I don't know, Matthew or Ray, if you want to say anything else. But I think, well, yeah.
Yeah, just very briefly to echo Mike's terms. Yeah, congratulations to everybody. Looking forward to this very much. I think what's fascinating about the topic is that it often tells us as much about ourselves as it does about potential aliens, and different people's views, which they hold very strongly about the existence or not of alien life, and what it might look like and what it couldn't look like and what they hope it looked like. I mean, this is as much a topic, I think, which is about our current state, the ideas that we have in our heads, as it is about the actual reality, which sadly, for the moment, is lacking. We've got one kind of life in the universe, and it's ours. And I think studying the potential there is for other kinds of life makes us reflect more deeply on the fragility of life on Earth. And whilst some commercial advocates of colonizing Mars seem very gung-ho about kind of trashing everywhere they go, I think maybe this might make us reflect upon the need to be extremely careful about where we go and how we go there, and what we do when we're there, in case there is other life, which might be very, very fragile.
Yeah, that's so true. Well, it's true that, as you said, Mike, this week we've taken the very first steps with Ingenuity on Mars. Today it was actually the second flight, and it was a success as well. So yeah, that's so true that yeah, we're on our way to explore the rest of the solar system at least. Ray, do you want to say anything else?
Yeah, I'd like to echo the echo in terms of my congratulations. I'm sure it's taken more effort perhaps than usual to work through this torpor of the kind of COVID, and you must have had some tenacity to put this together. So probably a lot has gone on beneath the actual surface. This is the kind of the end result of a lot of time and effort. Yeah, again, the interdisciplinarity of the field of astrobiology is pretty much represented in the cross-section of topics that are covered in terms of the presentations. I don't know if it was by accident or design that it's Earth Day today, so kind of thinking reflexively, as was suggested by Matthew there, that this kind of field of research, amongst other things, it helps us to kind of increase, to deepen our understanding of origins closer to home, as well as perhaps more distributed across the universe. So yeah, well done for getting to this stage. I'm very much looking forward to hearing what scholars pretty early on in their careers are focusing their attention on, and looking at their presentation across this range of topics during this session. So well done.
Yeah, thank you, Ray. Indeed, this is a very exciting times for all these things. I'm sure, well, as you see, the three of them always have some interesting stuff to say. So either if you are on your first year, either I mean, well, you can do it the RWL own unit pretty much any year. So I would really encourage you to do so, because this what you learn there, it's really valuable stuff, especially obviously if you're into this thing. But I think it's something that everyone should at least get an insight into, because it's basically what defines us as a civilization, as humans. I mean, this earth, and what astrobiology and SETI tries to find, it's basically what we are. So definitely, indeed, very important. So thank you to the three of you, and even if it's still 15 past 4, I don't know if our first presenter will be good to go. I believe she will be. So well, I would like now to then start with the Congress itself. So I am going to be introducing the first presentation, which will be done by Xiao Liu. on exploration and reflection on extraterrestrial civilizations. And Xiao, are you ready to share your screen and let us know what you have to say?
Yes, I'm ready.
Hello.
Hi.
Yeah, well, go ahead whenever you want.
Okay. So I'm going to share my screen now. Hello everyone, my name is Yao and I'm from Division of Dentistry. Today I would like to share some of my understanding on extraterrestrial civilizations. One day I was watching a famous Korean show called My Love from the Stars. The hero is a handsome man from another planet, probably because he was so handsome that he gave me endless fantasies about aliens. Maybe they are not always brutal or militant like in Avenger or Star Wars. Maybe when we are looking at distant planets, they are also looking at us. We gaze at each other in a vast universe. Don't know whether you also have this romantic imagination. We humans are so curious that we tried so many years to look for extraterrestrial civilizations. Initially, Cockney and Morrison proposed the use of radio to search for extraterrestrial civilizations. The subsequent introduction of OSMA program and the famous Drake equation contributed to the rapid development of this SETI in 1960s. Although the National Space Exploration Program was still funded to varying degrees in the 1970s and 1980s, there were still many who viewed the search for aliens as nothing more than a useless study. In 1971, NASA initiated the program Cyclops to study the conduct of the SETI project, noting that a dedicated of large telescopes array could be built. Ultimately, NASA canceled the National Space Exploration Program in 1993 due to a variety of social factors. The SETI project found nothing. It was obvious that the reason we had not yet found traces of those civilizations was that they didn't know of the existence of us. So in 1970, this METI project was launched. And in 1974, the first interstellar radio message was sent to M13. And the SETI project has received renewed attention in recent years as more Earth-sized planets have been discovered. And in 2016, Stephen Hawking launched the Breakthrough Listen project. This project uses the world's largest telescopes, such as Green Bank Telescope and Parkes Telescope, to maximize their role in the searching for extraterrestrial civilizations. This year sees the planned launch of James Webb Space Telescope, which will also make great progress, I think. And exploration and extrapolation about extraterrestrial civilizations is largely based on the Drake equation, which is used to extrapolate the number of highly intelligent civilizations that can communicate with us by radio. Despite the wide acceptance of this equation, the parameters in it are difficult to estimate. We can only rely on our existing knowledge and observations. However, on other planets in the universe, life may form and operate in a completely different way on Earth than on Earth. Based on our current estimates, these errors are on the order of magnitude. Based on the direct equation, scientists have been proposing methods for estimating extraterrestrial civilizations, and new modeling approaches have also been proposed to address the shortcomings of this equation. As we have seen, the exploration of extraterrestrial civilizations have been debated since early times. two of the most important issues are whether humans should actively search for them and whether we should send messages to them. The strongest objection to whether the SETI project should be undertaken is the issue of funding. Many believe that this research is nothing more than a collection of money from the taxpayer. The current solution to this problem is to share the data for SETI data analysis while the back-end equipment is engaged in other observational tasks. It is also argued that if there is no other civilizations in our universe, there is no need for this research to be carried out. The Fermi Paradox is a classic doctrine that essentially reads, if there is indeed a large number of extraterrestrial civilization in the galaxy, why have we not found any evidence of them? Also, fear of extraterrestrial intelligence loomed large. Right after the release of METI project, Martin Rowe had issued a statement including that beings from outer space could pose a threat to humanity and called for a ban on further messages. This view is supported by many scientists who believe that we do not know whether extraterrestrial civilizations are benevolent or brutal. Today, fears of aliens are growing, fueled by many science fiction films that the arrival of aliens could pose a threat to Earth. The exploration of extraterrestrial civilizations is undoubtedly a project of profound significance. When confronted with such a groundbreaking project, it is important it is impossible not to have any doubts. Scientists working on the, for example, scientists working on the atomic bomb were not sure whether their experiments would be successful, and the government also did not know whether they would get a return on their investment. Countless such experiments have been carried out. Some have success and some have failed. I think this is what science is all about. Science, more than just repeating the research of those who have gone before us, it is about being brave enough to explore. And we should definitely cautious about extraterrestrial civilizations because our technology, we may not be able to deal with the disasters they bring. However, I think we should not give up exploring them, as such exploration can bring us endless knowledge and bring us closer to the truth. That's all, thank you.
Thank you so much. Yep.
Okay.
Is that okay, Marco? Yeah, thank you so much. That was really interesting, actually. Can you hear me now? No. Can you hear me now? No.
It's very faint. I think you need to be closer to the microphone.
Okay.
That's better.
Okay. So yeah, thank you so much for the presentation. I was saying that that was very interesting, and I'm not sure if any of the people have any questions. I do have one. My question is, I mean, I've enjoyed, but I wanted to ask you about your opinion on this. So, you think we should be either undertake SETI projects or send messages out there?
For me, I am quite curious about this topic, and I think we should continue this project because it's have great meaning. And I think all the scientific research on this Earth have some drawbacks and we don't know the drawbacks before we see the outcome. So we shouldn't be so too much cautious about the unknown outcome. I think this is my opinion.
Yeah. I mean that makes sense in the end. Scientific progress in general works in that way. Don't know if anyone else have any questions. If not,
I don't have a question, but
yeah,
I've
sure.
got a kind of comment. So I really like the start of the presentation because, as is so often, whenever anyone gives a presentation on this topic, I always learn something just because it's a different viewpoint. And I thought your point about sort of alien civilizations potentially being sort of very attractive to us or wonderful in some sort of way, I think that's a very interesting kind of perspective, because often the perspective is quite negative, at least in film and sort of other sort of cultural activities. So I find that really, really interesting and an important thing to think about.
Thank you very much for your comment.
Yeah, that's totally right. That's true. We usually tend to present the other view of what that's so true. What if anyone has any other questions? Thank you, Sijao. That was very enjoyable. And next up, it's Sam. Are you ready? Well, I will introduce Sam and her presentation. I'm talking about Samshiska Raviraja. I'm not sure if I'm pronouncing that properly, but she's going to talk about rapid linguistic categorization and analysis for a time-sensitive framework to create a mode of communication between human and alien. And are you there, Sam?
Yeah. Can you hear me all right?
Yeah, we can hear you.
Awesome.
I know, and I will let people know that unfortunately your camera isn't working today.
Yeah, sorry about that.
But it's totally fine, and I guess that people will understand. There's no problem with that.
I am now going to present. Please tell me if you can view it all right.
That's
yeah.
working. Yeah.
Awesome. Great, thanks. So hello everyone, I'm Sam. I'm a first-year aerospace engineering student at University of Leicester, and I'm here today to present a very exciting research that me and my colleague worked on. From reading the title, you might be wondering, what does that even mean? Well, basically, if you guessed communicating with aliens, you guessed right. So this research aims to basically propose a framework for how we might have to communicate with them if and when we were to come in contact with them. So the project's going to look at it at the safer side of how we need to go about this kind of a situation, because we're going to be new to it. So this makes for a very interesting endeavor because of the mystery that it presents. Like if we were to imagine the horizons that we would open up if we were to have connections with aliens, we could probably learn a lot about science. Like maybe they have unlocked the mystery of immortality or advanced space travel or even time travel. So we have a lot to learn from each other. That would be a very interesting thing to look on. This brings us to the hypothesis of the project, which will be to use computational linguistics and AI, along with a combination of other linguistics techniques to not only analyze alien language, but to devise a method of having a back and forth long conversation with them. So give a background on why this is something worthy of pursuing. I have a few points here that I will go through very quickly. First and foremost, the safety of our species is what matters the most. We need to establish a communication to ensure that no harm will be done to both parties. We must also fully understand the intentions of their intentions and what they're capable of. This includes understanding what they know and how much they know about the universe. Like, for example, do they know how a nuclear physics works? That would mean that they might have knowledge to make weapons. Another thing to note is managing the announcement of alien contact to the public, as it might disrupt the relationship between the two species while, trying to negotiate what to do now. And the most important step after the entire risk assessment would be to devise a strategy on how we are to engage with them. Do we plan on talking with them only short term, or do we want to become an alliance of intergalactic species? So we can reduce possibilities to a binary model. Either aliens mean no harm at all to us, or they don't come in peace and have not very good intentions. Now we can move on to the design of a model for the algorithm. Before we move on, we must remain very objective, as the aliens might perceive the world completely different than ours. Even the way they see colors or dimensions will definitely affect how we want to communicate with them. As you can see, this is a basic breakdown of the algorithm to make it easy to understand. Basically, we would observe them, communicate with them, give them flashcards or videos and see how they would respond and react. That will allow us to understand if they are hostile or not, if they're innocent. And using that information, we can plan how we want to move on in the future. And another huge factor that we need to consider is their behavior and psychology, because that will tell us so much about how their mind works. Like, they might be innocent at first and they will learn a lot from us, and then they might turn on us. So we must ensure that we maintain a diplomatic relationship between the two species long term. To do that, we will have to use multiple linguistic techniques such as NLP and machine learning that will help us identify how their brain works. So we will have to use a combination of a team with psychologists and experts to having gadgets and equipments that will allow us to study their brain and activities. Moving on to their physiology, it is a very important thing because learning their biology will also help us choose which mode of communication we want to pick. Like, do they respond to light, or do they respond to sound? So, or a combination of light and sound. So if they can't see them, there's no point us trying to use our hands to convey anything. Even though there's no immediate need for such a framework, it is definitely worth having it now, because we have no idea when this might happen. It might happen tomorrow, it might happen next week, or 10 years from now. And currently, there is no framework laid out in anywhere for this. I mean, there might be something that the government has that we don't know about, but as a community of humans, sorry? Oh, thank you, thanks for that. And so basically, yeah, even though there's no immediate need for this, the research itself can help us in a lot of areas today. For example, we will be able to enhance the relationship between robots and humans for space missions by studying how we interact with species other than humans. And we will also be able to learn social behavioral patterns if we were to have colonies on different planets other than Earth. And it's, like, how do we interact with different environments? There's new things introduced, like a new species, or, like a completely different way of growing plants and stuff like that. And there are also non-space related applications of the concept. For example, making better equipment for people who have different needs for communication, such as people who can't see or hear. So we can use this research to enhance those technologies as well. And another interesting application would be to revive dead languages using computational linguistic techniques that we would have learned through this research. So finally, stage 2 is us trying to determine what we want to do. Do we want to form an alliance with them long term, or do we just say hello and then say bye? Because we need to ensure that they won't disrupt our species in the long run. Coming to the conclusion and limitations of approach, as any project, this also has limitations. And the biggest limitation is that we have no idea. There's no way we can anticipate what form they're going to come in, whether we can even see them or hear them. So we must allow some room for that kind of impossible possibility, because there's only so much we know about the universe. And we must remain very objective throughout the entire process. I'd like to thank the Astrobiology Society for giving me the opportunity to present this research, and also to mention my colleague who's not presenting with me right now, June, who worked on this with me. And here are the references for the research. I'm open for questions now. Thank you for your time.
Yep, thank you, Sam. That was very enjoyable. Oh, I'm sorry, Michael, were you about to say anything? Oh, true.
I will do that.
Okay. Yeah, but I was saying, yeah, thank you. That was very interesting. It's a perspective that I had never considered, to be fair. I don't know if our jury have it. Yeah, I see Matthew about to say something.
Yeah, it was very interesting, Sam, and very bold, very ambitious project you've got.
Yeah.
So one issue that strikes me is if you're going to be training AI and programs, you need to give them a data set to work on.
Yeah.
And you're going to hit a kind of, it's a problem in that, I guess, the only data sets you're going to have are those of human languages, which are all basically the same. They have differences, but so there's that question, how are you going to cope with that issue of not having a training set that is not human?
So that's a very good question. Yeah, sorry.
You might also want to think about maybe giving it some, as you said, some dead languages, things like Etruscan, which we still don't understand. Maybe you can get some insights into what's going on there. And finally, what about the issue of the conversation? Because you talked about conversations, but that seems pretty unlikely unless they're on Mars or Jupiter. That conversation is going to take a long time. It'll be hello, and then them responding maybe decades away.
I agree. So there are different scenarios that might play out. So either we run into them while we're on a space mission, or they come to us here. So obviously, if we meet with them here, it will play towards our advantage because we have our technology here, we have our workforce that will help us protect our species, but at the same time, we're also exposing our entire species to this foreign creature. So there's that risk. But going on to your other questions about the conversation, you're definitely right. We basically want to aim on basically like yes or no questions, just to ensure that there's no risk to both species. And regarding the, sorry, what was your first question?
It's about how are you going to train your AI if the only languages you've got are human?
Right, thanks for that. So yeah, initially, because we don't have anything to work on right now, what we can just do is sort of prepare with what we have. And what we have is just what us humans have done. And eventually, when it does happen, we are going, it's going to take a very long time. We're going to have to be very peaceful and have a lot of patience, come up with ways to see how they interact with stuff. So like things like, flashcards, but in a very advanced way, of course, not like how we make flashcards for toddlers, or like videos, or maybe even augmented reality kind of thing. So we can just see how they interact in a closed environment before exposing them out to the public that might pose a higher risk. So right now we don't have much to train the AI, but we can work with what we've got and work with some predictions. And eventually when it does happen, that's when we actually have some hard data to input. Does that answer your question? Sorry.
Yeah, that's great. Thank you.
Awesome. Thank you.
Yep, I think now Ray's turn. Yeah, go ahead.
Hi, thanks, Sam. Great presentation. I'm got a couple of kind of areas or topics I'd like to ask you about. One is what's your underlying model of communication? Is this largely kind of a Shannon Weaver information processing, or are you more pitched in kind of linguistics and semiotics? If you could provide a little bit of clarity in terms of like what model or set of theories and approaches do you bring, or is your research based upon? So that's my first chunk of my first question. My second one is about interfaces and mediating devices. You mentioned video, audio, flashcards. in what sense is your research considering the devices that are going to serve as an interface in order to establish some form of information with something that isn't human? So those are my two questions.
Those are very interesting questions. Thank you for that. So for your first one, basically the format of what we're going to study from them, it really depends on what they have, like physiologically, what they have. Do they have hands? Do they have eyes to point at things? Even like the very basic idea of if you were to draw an arrow mark, our eyes go to as a pointy end, but for them, they might not even recognize it's there. So depending on what they have, I guess that would allow us to determine, and also we would have to study their intelligence level. Are they do they have like pet-like intelligence, or do they have like really high intelligence? That will allow us to choose which format, whether they even have, do they even have a form of communication amongst their own species, or do they have like telepathy, for example. So there might be situations where we actually can't do anything because of just how the situation is and what their biology is. So yeah, again, that's the limitation of the project, as I mentioned. And moving on to the interface and the device that we can make for communicating with them. This also depends on, again, what they have. And definitely, I would say it's very highly likely that we will have to research a whole new technology just to like communicate with them. Like now we're communicating through Zoom, but with them, we might have to come up with a whole new system. So we would be lucky if they already have the intelligence and they have like, okay, we are really smart. We can make anything for you. There you go. So it might be as easy as that too. So yeah, I guess we work with what we get.
Great.
Yeah.
Thank you. That's great. Thank you very much.
Yeah, thank you, Ray and Matthew, for your questions. And if there are no more questions, which I think, oh, Luke has a question. Okay, go ahead, Luke.
Yeah, I just wanted to ask, just in your opinion, what do you think is the most important, like, first thing to say if we met another civilization or something like that?
Oh, that's very interesting. Probably hello.
Good start, I guess.
I mean, isn't that what we do? Like we wave our hands, say hello. So it's like the most first natural thing that we would do. But then they have no idea that's what we do. So they might just be like, what are you guys doing? So yeah. But the most important thing would be to say, hey, we're not going to harm you. Please don't harm us. So that would be the most important thing, I'd say. Yeah.
Great, thanks.
Thank you.
Yeah, I think literally establishing which could be the best way of approaching them. First instance, that could lead us to a whole 3-hour conversation for sure, and we won't even reach an agreement. What did you say?
Oh, I said yes, definitely. Yeah, that's a huge conversation. Yeah.
Yeah, it is. Well, if that's it, thank you so much for your presentation. It was actually very enjoyable and a nice topic, and I'm seeing some comments on our YouTube agreeing with what I'm saying. So thank you so much.
Thank you.
And now it's, as you said, your partner Drew turn. I'm talking about Drew Sinkby, and I'm not sure if I've pronounced that properly, but he's going to talk to us about the workings of society in an alien world. Drew, are you ready to present? I'm waiting confirmation.
Oh, yeah.
Yep. Hello, Drew. Okay,
hello.
Good to go. Feel free to share your screen whenever you want.
Yeah, just a minute.
Okay. Yep, that's working. And yeah.
Is it working?
Yep, it is working.
Okay.
Yep.
So,
there you go.
Yeah, I would like to talk about, I am Dhruv Singhvi, and I would like to talk about a society of a hacked evolutionary species. So in my presentation, I would like to talk about probably how evolution can hack itself and explore the possibilities of existence of alien societies based on those hacks. And just as a side note, I'm probably going through the main points of the presentation because of time constraints, but if anyone wants to, they can pause and read the points for the examples. So starting on, there are few limitations of evolution, as we all know. First of all, it's quite slow, as we can see from this example in this picture. Then it is slow because it's based on the approach of trial and error, right? So only those species survive which have those useful errors, and they pass on to the next generations. And the organisms that don't have the required characteristics to adapt to the new surroundings, they either die or they extinct. Now, since the evolution is based on this random trial and error approach, we can see that a characteristic could emerge in a species which could grant the species a property to make the whole process quick and predictable for themselves. We know that this could happen because that's the same that has happened on Earth in the form of human brains. Like evolution granted the ability of higher intellect to the human brains, and because of the high intellect, we made complicated and sophisticated tools to support our survival and growth. Now, today these tools have integrated so much in our daily lives that they have basically become like extended body parts. Now, yeah, they have become basically like extended body parts. So, in my viewpoint, for any life to qualify as intelligent or in the universe to qualify as intelligent, it should either find a hack in its evolutionary system and try to exploit it. Therefore, in moving in the further part of the presentation, I would like to discuss two such hacks and analyze how would an alien society based on these hacks would work when compared to a human society. Now, before talking of alien societies, let us define on what are the pillars on which the human society is based. According to me, the pillars of a human society are emotions, which are mostly controlled by the chemicals in our brain. Then there is social behavior, which is mostly determined by things like groupism. Then there is means of communication, which includes from language, money, internet, economies, etc. Now, before moving on to a first hack, I would like to discuss a scale called as the information transfer and storage scale. So evolution is not only about replicating and making a similar copy, it also involves the transfer of valuable information from the parent to the offspring, basically intergeneration information transfer. With the evolution on Earth, we have seen a clear pattern involving the transfer and the storage of information as the evolution has progressed. And I have divided this into 5 levels. The first is the genetic memory, which involves the information stored and the transfer of it in the form of genes. Then there is organ memory, in which the information is stored in organs and it's transferred by dictating what the organ should do. Then there is a memory stored in the brain in the form of experiences and emotions. Then there is cultural memory, which involves history, religion, books, etc. Then there is digital memory, which is internet, basically digital clouds to store information and transfer it. So if we consider humans, then we can see that humans inherit both level 1 and level 2, which are the genetic and the organ memory from our parents. Now let's come to the hack. The hack is that if ever a species ever emerged with a transfer information level up to level 3 or level 4 with that efficiency biologically, then this would be a hack. It would be a hack in my viewpoint, because now the species can not only transfer more amount of valuable information apart from the genetic structure, but also it can transfer the valuable characteristics that can help it to change to very rapid changes in the surrounding. Like for example, the parent can consciously create some characteristic for itself and then pass on to the next generation. Therefore, allowing the parents for the transfer of considerable characteristic of their choice in the generation itself, thus speeding up the process of evolution and making it basically less based on trial and error, but more guided by the parents. So one of the important consequences, if ever a human-like species ever emerged on a planet with this hack ingrained in their biology, we can see that then the parents would not only be transferring their genetic information, but would also be setting the emotional intelligence skill or behavior or psychological, etc. mindset of the offspring. So in simpler words, I can say that the structure of the offspring would be heavily dependent on how the parents led their life. Now let's go on to how would this society function on the basis of emotions. The society would encourage positive emotions just because of the fact that the next generation would inherit the mindset. If the parents have a positive mindset, the child has higher chances or a stronger chance of having this positive mindset. now the older members of the society, the members of the society who have passed through the phases of reproduction, they have more human-like emotions. They would probably have the three components of emotions: positive, neutral, and the negatives. They would try to involve in all the deeds that they have never that they would be themselves in a way, be more human-like. Then coming to the social aspect is that just like we have ethnic groups in humans, that society might have something called as the combination groups, in which the individuals believing in it would consist of individuals believing that specific combinations of values and skill sets would be the best for the specific offsprings. Also in that society, I believe that a monarchy or a dictator would be controlling everything would make more sense than democracy, because if the king has some is a good, or like has good values, then his successor would also inherit the same positive values of the king. Now, the third point of the social aspect is that since the section of the society who have passed through the phases of reproduction, they would suffer something called as the midlife crisis that we do have here on Earth, a sense that they don't have any purpose in life. Now, the earlier purpose of them to live was fulfilled by the to instill the desired values in the offspring, but once it's done, they would feel no purpose to exist. Now, human history has taught us that whenever there is a lack of sense of purpose, or there are any gaps in knowledge, it's usually filled with the concept of religion. Therefore, existence of an alien religion might be a real possibility. Now, the third is the means of communication. In my viewpoint, if there is any intelligent life or any kind of life anywhere in the universe, the only way it can communicate with each other is through a transfer of some kind of energy. In humans, through speech, we do this by the exchange of sound energy. But when it comes to something like called money, we humans made this fictional energy called money for better and efficient communication between the individuals. So in that society, probably if they don't have something as actual energy, they might come with a concept of fictional energy to make the communication way better. Now, for the second hack, I would like to consider a concept called as a hive mind. A hive mind is basically a number of people, a large number of people who either share the knowledge, opinions, informations with each other, basically like a collective intelligence. Now, on Earth, in a way, hive mind has existed in us in the form of of our nervous systems. The cells in our body are connected by the electrical signals produced by the neurons, and this development of this extensive nervous system is one of the main factors that contributed to the development of the human brain. So consider this, right? A hive mind at the neuron level has laid down the foundations of modern humans by the development of with the help of the development of the human brain. Now consider what a species can do if a hive mind structure is achieved at a whole species level. Now, a planet, a planet where, like, let's say a human species evolved, and sorry, yeah, sure. So let's say a human species ever evolved in this planet, and we have different passage of time. Now, evolution granted the species to have a biological hive mind. Now let's consider how would they how would they perform on the different aspects of the society. Emotions. They won't have specific emotions because they don't have the feeling for struggle and jealousy. Because once if everything is equal, you won't feel. The developments of the human society is based on selfishness and jealousy. A hive mind doesn't have those, so it would basically the biology would never ever instill the emotions of jealousy and selfishness in the hive mind society, because everyone is connected to each other and basically everyone is the same. Now let's come to the social aspect. One of the reasons why communism never worked on Earth is because humans are selfish, and in the hive mind, it's a perfect society. So it uh, the communism is probably the best system that they could ever come up with. So it might be the ultimate communist utopia that the thinkers ever thought of. And it's also important to note that the processes that would happen in that hive mind society would be similar to Yeah, sure. Just the last point would be similar to the process happening inside the brain. So yeah, and the means of communication would be same for exchange of energy. Thank you. Yeah, thank you. I should stop sharing screen.
It's okay. I mean, if you need to add any last words, it's okay.
Oh, no, it's fine. It's fine.
That's been very interesting. Another presentation. I see that the University of Leicester has a very great representation here today, with you both, you and Sam, and that was very nice actually. I don't know if our jury has any questions for you. Or anyone. If not, we will carry on. And I've seen you've left your email there. We will also, well, I mean, for whoever is watching this now, either now or in the future, as this will be in YouTube forever, if you want to direct any questions to the speakers, feel free to email us basically anytime, and we can put you in contact with them, which might be useful for future visualizations of this Congress. So thank you, Drew, and Luke, I think it's your time to carry on.
All right, sure. Next up, we have Salma Malaika with the presentation, Alternative Biochemistries, Are Our Molecules Not So Universal? You ready to go, Salma?
Yep, thank you.
Great, sure.
If I can just have a second to share my screen. Oops. Can you see that okay?
That's great, yeah.
Okay, perfect. Thank you. Okay, so hello everyone. My name is Salma Malaika. I am a year 1 BSc Biology with Japanese student at the University of Manchester. And today I'll be talking about alternative biochemistries and extraterrestrial life forms. So I'm not sure if I can make it a fuller screen, like even more than this. I don't know how to. I'm sorry, I hope that's okay. Okay, so DNA, for example, is often referred to as being a universal genetic code. And I'm sure many of us here agree that the term universal might be a bit generous because we are only familiar with one type of life form. So today I want to discuss possible alternatives to what we are familiar with. But before I start talking about things on a more molecular level, I do want to introduce a thought that I think you should keep in the back of your head throughout this presentation. So if I tell you to imagine that you're eating a piece of cheese, and I ask you to explain what this piece of cheese tastes like, you'll probably say, well, it tastes salty. But imagine someone who has only ever eaten from this block of cheese their entire life and has never been exposed to any other type of food. That person will probably not have the capacity to decipher what taste modalities are or what salty even is, because they can't compare it to any contrasting flavors like sweet, spicy, or bitter. So with that being said, I want you all to imagine that we are this person and Earth life is this block of cheese. Because we don't know anything else, we probably have no idea as to what kind of other life forms there will be outside of Earth. But that's just a thought to keep in mind for now. I would like us to try and hypothesize what these other taste modalities would be like. So first of all, I'm sure many of you are familiar with how absolutely essential water is to all life forms. And that's mainly because of its chemical properties as a liquid solvent. It's even sometimes called the universal solvent. So just to give an example, water is a polar molecule. So the oxygen atom is partially negative and the hydrogen atoms are partially positive. And that means that molecules that are important, such as nutrients, can dissolve in water, and water kind of travels throughout a living system and distributes these nutrients to organelles, organs, or cells that might need them. So that's just one example of how essential water is. some scientists agree that the most viable alternative to water is ammonia. So ammonia, just like water, is polar. I think it is worth mentioning that ammonia only is liquid at much lower temperatures. So its water-like characteristics are only at lower temperatures, which means ammonia-based life forms might lie way beyond the habitable zone. And some scientists think that that might mean that species evolution would be rather slow because chemical reactions and metabolisms are quite slow at lower temperatures, but I digress. So similarities to water, it's polar, it dissolves ions, it dissolves salt, it dissolves organic compounds. And one thing that is quite striking is that ammonia related, water related organic compounds have ammonia related organic compounds that are analogs of each other. So basically what analogs means is chemical correspondence. So this is the amine group, the hydroxyl group of an organic compound is replaced by an amine group in an analog. So this is just an example. So here we have ethanol, which is a water-related organic compound. And this is how the alcohol might look like in an ammonia-based world. And I think this is quite important because first of all, hydroxyl groups are very important because they can form intermolecular hydrogen bonds because you have the partial negative charge of the oxygen attracted to the partial positive charge of another molecule's hydrogen. And that's quite important for stability in molecules. And it's also important for forming bonds. Here we have two amino acids, and that is a peptide bond that is formed through the use of removing a hydroxyl group. And these forms proteins, which are very important for bodily functions. So in an ammonia-based world, this might be possible. Also, ammonia has amphoteric characteristics just like water. So what that means is that it can act as both a base and an acid. So as you can see here, this is the acid form of water, and this is the ammonia-based analog, same for the base. And this is extremely important because amphoteric characteristics means that it opens up a lot of possibilities for chemical reactions and different chemical reactions in the body. So that's quite important. So now I would like to talk about the next alternative biochemistry, which is an alternative for carbon. So carbon is an extremely important molecule. It has 4 valence electrons, which means it can bond to 4 different molecules itself, other molecules, single, double, triple bonds, huge variety. And a lot of scientists agree that a viable option could be silicon. So silicon is the next on the periodic table, right? Same group, 4 valence electrons. It might be a bit counterintuitive that if we go back to early Earth, the silicon to carbon ratio was 925:1, yet life still evolved with carbon instead of silicon. However, that might be because of the certain attributes that Earth had at the time rendered it a lot easier for carbon life to arise instead of silicon. For example, the amount of oxygen in the crust could have turned the silicon to silicates, and that's extremely unreactive. So we might have to consider different combinations of biochemistries that can allow for silicon-based life. So Earth life respires in an oxidizing atmosphere, so an atmosphere that has oxygen, and produces carbon dioxide as waste. So this is carbon dioxide, so carbon and oxygen. Silicon, on the other hand, might be able to do so in a reducing atmosphere because an oxidized silicon, is not soluble until 1,600 degrees Celsius. It is a solid, which is not going to work as a waste. So this is possible. Another possibility is that carbon is a liquid water based, life is in liquid water. However, silicon would not work in liquid water because this is an analog to hydrocarbons, and it is extremely reactive in liquid water. However, liquid nitrogen, which is a much colder liquid, might be able to sustain something that is so reactive. And another argument to this hypothesis is that polysilanols, which are the silicon version of sugars, are actually soluble in nitrogen. So with that being said, even with all of these seemingly viable hypotheses, I do want to take us back to the cheese analogy, because if someone who has never tried cheese, other types of food before, sees an onion, they wouldn't know that cutting into an onion would actually allow you to cry, which means it elicits not a taste response, but a different kind of response altogether. So I think we can all agree that without a second known instance of life, extraterrestrial life could be something that our psychologies cannot even remotely decipher, or our technologies cannot even remotely detect. So thank you very much.
Thanks very much. That was really interesting.
Thank you.
If anyone has any questions, Matthew, go for it.
Yeah, I mean, there is this idea that it's already here. So part of the interesting thing, of course, is that one of the main ways that we detect the existence of life is through the presence of nucleic acids using PCR. But if life isn't using DNA or RNA, then that wouldn't be picked up. So, for example, there's a whole book. It's called Weird Life. I think it's in the university library. You can get a copy of it. It's well worth reading it. It's a mixture of the bonkers and the thought-provoking about whether there is such a thing. And one of the signs that's often suggested is something called desert varnish, which appears on rocks in the Arizona desert, and it doesn't seem to be organic, and it's been claimed it has no known geological explanation. However, I was watching the Perseverance feed the other day, and they were pointing out that the rocks on Mars have desert varnish as well. So either weird or maybe it's just some weird geology. Anyway, that was a very interesting and thought-provoking talk. Thanks a lot.
Thank you. Thank you so much.
Gibet, do you have a question?
Yeah, actually, I would like to ask Salma if you really think that a life based on silicon could be possible. I mean, in the sense of a system able to replicate itself.
Oh, do I believe that it is possible?
Yeah, I mean, you've talked about the biochemistry and about the solvent, but do you really think that that could mean that a living being could be made of like molecules of silicon?
I see. I think I do believe so. I do believe that it's very possible, and I think that a lot of the times our opinions are very relative to what we know. So it's possible that even different life forms that are extraterrestrial life forms might be completely different in the sense that their ways of self-replicating are not quite familiar to what we know, or they have a different type of evolution, or maybe evolution is something completely different that we are not aware of, that we actually can't put words to. So I think for me personally, whenever someone asks me, do you think for example, a silicon-based life would be able to do this or would be able to do that, I feel like it goes back to the cheese analogy, that it could be a life form, but it could be replicating in ways that we can't know or we can't detect, or that we can't be able to decipher just based on what we know from how these molecules work together. So I do think it's very possible, and I think because there's something I really love, it's that if all the sand in the earth, of all the oceans, of all the deserts, was the universe, the sun, which is over 333 times the mass of Earth, would not even register as a single grain. So I think with that vastness of the universe, there could be maybe even life the same way as we know it here, maybe multiple different types of life, I think is possible.
Great, thanks. Any other questions? Joaquin, I guess.
Yeah, thank you for your presentation. I think that was very well structured and with lots of interesting information conveyed in one single place, which is kind of difficult to find because obviously there are all these papers talking about either one or the other, but it's been a great summary and a great overview of the whole thing. I guess that my questions were, well, I have two of them. One is I guess that, well, I guess I don't know if during your research you came across where we could find these forms of life, or either based on any of the possibilities you have explained to us. So I don't know, did you come across any of these let's say astronomical bodies where we could find this like different biochemistries?
So I did not necessarily look into where we can find these, but I did. A lot of these papers stated things like maybe we shouldn't be only looking at the habitable zone, for example, for habitable life, or maybe we should look at specific temperatures for where liquid ammonia could exist, or specific temperatures where silicon-based life can happen at liquid nitrogen. So I think just knowing how these chemical combinations and biochemistry combinations could work out, and using that information to find like celestial bodies in general that have the right temperature, the right size, the right pressure, I think that is quite important.
Okay, yeah. I mean, yeah. At least in my opinion, you're totally right. And my other question was more in terms of, so obviously, I agree with you. Well, as much as I know, in that there might be other different biochemistry that life could have explored elsewhere in the universe. But what about complex life? Because I guess that you've been talking. I mean, these biochemistries can at the very least, be applied to extremophiles or small organisms. But what do you think about more complex organisms? Do you think we could expect to find human-like or animal-like shapes or life forms based on silicon, for example?
Yeah, so I think I do have a tendency to look at things on a molecular level, but when I think about how vast the universe is and how these seem quite probable because of the similarities they have to our chemical combinations, I would like to think that there's probably somewhere out there, or at a different time as well, probably possible, that complex silicon-based life was able to arise with similar chemical properties to how carbon-based life is like. So I do agree, and I do think that it is possible for complex life with different biochemistries to exist.
Okay, thank you so much. Yeah, very interesting.
Thank you.
Great, thanks. If we have no more questions, then I guess we can go on to the next presentation. So next up, we have Ilan Elavarasan, sorry about that for butchering your name a bit, with the title Fungi for Bioremediation of Martian Regolith for Future Space Habitats. Ilan, are you ready to go?
Yeah, hello, can you hear me?
We can hear you.
Yeah, so yeah, I'll be sharing my screen shortly. Can you see my screen?
Not just yet. Oh yeah, can now. That's perfect.
Can you see my screen?
Yes.
Just bear with me because my internet connection is quite slow.
Mm-hmm.
Yeah, so thank you for having me at the Astrobiology Society, the Congress Frontiers Award. Shortly, I'll be presenting on fungi for bioremediation of Martian regolith for future space habitats. So I'm Ilankurali Ilavarasan, and I'm a research associate at Space Development Nexus India. I'm an aerospace engineer and aspiring to become an astrobiologist. So I'm working on a novel research in India, that is, this involves the analysis of composition of Martian regolith for viability of fungal cells to assist in plant growth, basically, and also the potentiality of mycelia in initiating food production through the regolith that is obtained through ISRU techniques when a space habitat is established in Mars. So this comes under the domain of planetary habitability. So the need for my project is that when we settle on Mars in future, there will be ISRU techniques which are inevitable, and it is very essential, and it directly extrapolates to the use of regolith for plant production, which in turn helps us in food production, oxygen, recycling of organic materials to produce fuel, etc., etc. But there is a what if and but in all the space exploration scenarios. So in this project, the big what if or but is that there are lots of SCPs and GCR particles which are they are soaked the Martian regolith because of the less radiation environment. That is, we all know that there is no less thin atmosphere of Mars, which is less than 1% of Earth's atmosphere. It directly means that there are lots of toxins, that is perchlorates, present in the soil, which make it unfit for plant growth. So I'm going to cover what will be the essential methods or need to bioremediate the Martian regolith obtained by ISRU for plant growth, and that is done through the fungal or the mycelial network. So I've compared few parameters which are required to grow plants on Earth, and also the Martian conditions, and I've compared it over here for to get to know how plants can be efficiently grown and which parameters are more important and had to be rectified here. We'll come back to the slide when all the points are sorted out. So we are going first. I have taken the radiation exposure of the surface and subsurface penetration. So we all know that there is a thin Martian atmosphere, and there are highly energetic cosmic radiation which are able to penetrate the Martian atmosphere and even to the subsurface at some level. The main contributors are the GCR, the galactic cosmic rays, and the sporadic solar energetic particles, that SCPs. The Martian atmospheric composition is basically of carbon, oxygen, nitrogen, argon, etc. And 95% it is composed of CO2. And we have the exciting news of MOXIE, which is equipped in Perseverance rover, which have successfully converted CO2 of Martian atmosphere into oxygen. So all these techniques will be involved in a space habitat on Mars in future. But there is the radiation environment of Mars consists of majorly hydrogen and helium particles, that is more than 90%. And sometimes they reach the subsurface too, but the water ice which is present at the subsurface shields some amount of radiation. So this means that the surface regolith is less efficient than a subsurface regolith. It means that we have to get access to the subsurface regolith through ISRU techniques. I've given the characteristics of the subsurface over here. It's hyper arid, and it also has extreme temperature variations, but there is also formation of brines due to the presence of various salts, namely perchlorates, sulfates, chlorides, carbonates, and nitrates in the Martian atmosphere. So this is the radiation environment of the Mars, where the primary particles enter the atmosphere and the secondary particles are able to penetrate the subsurface up to some level, and even to the subsurface sheets. Few particles even able to penetrate the subsurface sheets. So even if the Martian regolith is obtained from the subsurface sheets, there are presence of particles which are inefficient for plant growth, and this is the radiation level present on the Martian atmosphere, and it is compared to various other phenomena we observe on Earth. This is a experiment which is made on Earth to measure the amount of GCRs and SCPs and how much unit is observed on the surface, and how we can make use of the amount that we gain knowledge from Earth, and one day establish it in the space habitats for plant growth or for human settlements. we have covered that we have to use the subsurface regolith, but what the presence of so the presence of nutrients is much more important for plant growth. Some of the nutrients which are present or minerals present on the subsurface or near surface are silica, phyllosilicates, sulfates, etc. And there are also hydrous minerals, which is a big plus point for Mars. And also there is presence of chloride-bearing salts because of the following activities like hydrothermal brines, meteoritic water impact events, degassing of volatile elements, and heated ash deposits, etc. So this is a map for to select the sites from which we'll extract minerals. And how does fungi come into the picture is that I have used the hero of my project is the melanin pigment. So all these references I've given here are already done on Earth, where fungi has thrived in the extreme environments, even in some spacecrafts where there are conditions which is extremely high. For example, high salinity, high radiation, limited nutrients, extreme temperature, etc. So we can directly extrapolate this to the Martian atmosphere and relate that fungi, it fulfills all the category needed. So this is the basic needs for a plant growth. Example, alkalinity, nitrogen, addition of calcium perchlorate, etc. But fungi satisfies all these conditions, especially the production of cryoprotectants like glycerol, trehalose, and in the melanin fungi. So this will be the methodology where we follow the three different methodologies, like we can bombard the DNA strands of specific fungi with ionizing radiation consisting of heavy particles like helium, nuclei, etc. And we'll be able to augment the Martian simulant regolith or the bedrock minerals like phyllosilicates, carbonates, etc. for plant growth and check the viability of growth of mycelia, and also the technique of biofertilization or controlled environment agriculture, where we will use appropriate regolith and bedrock simulants as a plant growth medium. These are the methods involved, which are sample preparation, survival assessment, DNA integrity test, and the fungal melanin extraction to see how the fungi have coped up with the environmental conditions through spectrophotometric analysis. So the bar graph which we would get from it would look like this. Some of the species viable which we have chosen are Ascomyta fungi, Cryomyces antarcticus. All these are extremophilic fungi or radiotrophic fungi which can withstand the radiation and have proven on extreme conditions on Earth. These are the two type of Vangelia dermatitis and Cryptococcus neoformans, which known to consist the pigment melanin, one which can naturally produce it and one which can be induced to produce. So some of the fungi experiments are already being tested in the space. For example, the CFS-A colored fungi in space experiment, which involves Ulocladium chartarum, Aspergillus niger, Cladosporium herbarum, Basipetospora halophile. All these have different chemotypes and different environmental conditions on which they grow. So we can tabulate and use different specific types of fungi, biogenetically engineer it, and use for the future space colonizing space habitats. Some of the extreme environments where we tend to collect soil samples, one is Ladakh, which is very similar to Mars environment. We can see in the background there is hyper-aridity, saline conditions, and also there are presence of stromatolites, which are all examples of how extreme the conditions are. Another one site is the Lunar crater, which is a meteoritic crater which is very similar to Mars, present in Maharashtra, India. So some of these sites were selected for soil analysis, and this is Habitat Mate, Mars analog station present at Brazil. I'm a current researcher where they'll be sending soil from the Picajo Kabugi or the Kabugi Peak, where soil analysis is done, the research on food production, etc., which will be done on Mars habitat is simulated over here. So I'll be getting soil from the soil of Mount Pico di Kabig, which is an extinct volcano, and the simulant soil is very much similar to the Mars regolith, and it will be helpful for us to simulate the conditions on Earth and test the viability of fungi for plant growth. why is the need for a bioremediation of Martian regolith is that we are in a space era, which is also called as the space reconnaissance, where our horizons will tend to go beyond our planetary neighborhood to make humanity an interplanetary species. So I put forward the current technological trends, especially in AI, automated integrated systems, making science an interdisciplinary arena. For example, this project involves various subjects like biology, biochemistry, geology, geochemistry, etc., even geochronology, etc., into single projects. So this means that science is very interdisciplinary, and when different fields come together and fuse, we'll get the beauty of space exploration. So synthetic biology in space is that we don't have to pack everything we need to go for a space mission. Just we have to pack the enough bacteria to build things for us. So thank you for listening to me. That's the end of my presentation.
That's great. Thanks very much. That was really interesting.
Thank you.
If you want to stop sharing your screen, we can go to questions now. Does anyone have any questions? Matthew?
Yeah, I think that's very interesting, and clearly you have really grasped the science and the potential there for growing mushrooms on Mars. But there's one aspect, you talked about things being multidisciplinary or interdisciplinary, but there's one aspect which you've kind of left out, and I'd be interested in your thoughts a bit about this. What about the ethics of this? What about, I mean, you take it as a given that we're going to go to Mars and live there and grow things in the regolith, but what evidence would we need to have that Mars was sterile, that there was no life before we could do this? And even if we did know that Mars was sterile, who should decide that we would then start growing things and kind of terraforming it? What's the politics of this? Because this has a politics, and by not including it, you're letting a particular view creep into your view and your project.
Yes. So I've left out the word, as you mentioned, like abiding planetary protection. So we know that it is inevitable that planetary protection is the need of the hour. So of course, politics is involved in this. Unless we consider humanity as a single species in a planetary scale, aiming to expand its horizon, its knowledge, its curiosity, and taking it to the next level. So this, personally, I believe space exploration makes people unite. When sustainable goals can be achieved in space exploration, it can be directly connected to Earth. It can form a solution for earthly problems. Take it climate change or agricultural development, sustainable development for a peaceful future, etc. So I say it in this scale, where when we abide the planetary protection and creating a home for humans, where we can use another planet, but to make aware of, to bring awareness among people that if we can terraform a planet, another planet, why can't we make our living home a better one? So it all falls in this one circle where there will be more awareness if we take this to a next level.
Okay, thank you.
Anyone else?
I just wanted to say that it's been an interesting presentation. I don't have any proper questions, but it's been an interesting perspective, and congrats for being so into the topic and explaining it very clear. Thank you so much for that. Yeah.
Yeah, I just want to add that I found it very inspirational. And if we do become an interplanetary spacefaring species, it'll be because of people like you. Thank you.
Thank you. Thank you.
If that's all the questions, we're going to have a quick 5-minute break now until 5:35. And then after that, we'll be back with Vikas. So thanks, everyone. See you all in 5 minutes.
Yep. See you in 5 minutes. Okay, I was waiting for your confirmation actually. So welcome everyone for the second half of this Frontiers Award. So we have just 5 presentations left, and I'm not sure if it's my turn or yours, Luke. I think it's mine. Yeah. Okay, it's mine. So our next presentation is going to be delivered by Vikas Mishra on space colonization. Vikas, are you there? Ready to present?
Yeah, I'm starting presentation.
Yeah, sure. If you can share your screen and if you can turn your camera on, that would be great as well. So people can see you. Okay, that seems to be working, even if it's my face there. Okay, yeah, that's working.
Good evening, everyone here. Today I'm gonna talk about space colonization. That is myself, Vikas Mishra. I am currently doing computer engineering. So I'm going to talk about space colonization. Space colonization is creating permanent habitation and exploration of natural resources beyond Earth. But why we need to do space colonization and why we need to make life multiplanetary? The Earth was subjected to 5 major extinction events, and a 6 mass extinction event is ongoing. Holocene extinction, which is result of human activity driven by the population growth and the overconsumption of Earth natural resources. Multiplanetary life is the solution to the Dawkins argument and will decrease the likelihood of a life extinction. If we can make life multiplanetary, there can maybe come a day when some plants and animals die out on Earth but are still alive on other planets. In another half billion years or so, the sun will expand and the life will be impossible on the Earth. We need to establish a multiplanetary society by then, or humanity will cease to exist. Okay, before we jump to space colonization, one of the most profound questions for the mankind: does life exist beyond Earth? If life exists beyond Earth, then why we haven't found alien yet? And the hunt for this question and the human curiosity about space and alien life led to the numerous discovery about our universe. So why we have not found alien yet? Are we alone in this universe? Is the life on the Earth first, but may not be the last? Are we looking in the wrong places? Maybe alien life are too advanced and they don't bother about us, about a type 0.7 civilization, or they may be made up of a different biochemistry, not maybe a carbon based, it may be a silicon based or an inorganic, or maybe robots. Who knows? Could alien life be too far away from life that light may have not reached us? Is our technology not capable to trace alien life? Uh, our, our civilization stand at 0.7 on the Kardashev scale. Now, what is habitable zone? The habitable zone is the area around a star where it is not too hot, not too cold for a liquid water to exist on the surface of the surrounding plant. The rocky exoplanet found in the habitable zone on the star are more likely targets for the detecting liquid water on the surface. So if we want to colonize planets, we need to colonize the planet which comes under habitable zone. We can colonize other worlds in 2 ways: terraformation and paraterraformation. Terraformation is a process where we modify the atmosphere, temperature, and surface topology and ecology of any other world similar to Earth. Paraterraformation, also known as warehouse, is a concept of building many connected airtight bubbles. Before we could colonize our universe, we must start with our solar system, right? So which planets and moon may support life? Moons like Europa, Andromeda, Titan, Io, Triton, Dione, and Charon shows the potentiality for hosting life, in which Europa and Enceladus shows the highest possibility. But if we want to explore further, we must start with a Mars. But why they show the possibility of hosting life. Titan is characterized by the hydrocarbon lakes, facilitates and it have facility of the complex organic molecules. Callisto have a subsurface ocean heated by the tidal waves. Granite have a magnetic field with the ice and a ocean stacked up in a several layer with salty water has second layer on the top rocky iron ore. It is subjected to intense tidal heating, which makes it most volcanic active object in the solar system. The outgassing generates a trace atmosphere. Titron may have a large layer of water or a subsurface ocean. A Dion may have an internal water ocean under the 100 km of a thrust, possibly suitable for microbial life. Kion may have an interior ocean of water and ammonium. But as I said, Europa and Enceladus shows the highest possibility of hosting life. But why? Europa have a vast interior ocean beneath the surface maintained by the geological activity, tidal heating, and irradiation. The ocean water itself and even upper ice could be potential inhabitability. The Enceladus have a subsurface liquid water ocean due to the tidal heating or a geometrical activity. Free molecule hydrogen has been detected, providing another potential energy source for a life. Also went on the floor of its subsurface ocean, similar to the Earth's when life originated. Also, we have just mapped 5% of our ocean surface. So there may be an alien life on the Earth beneath the surface. Colonization of Mars. If we want to colonize our solar system, we must start with Mars. But why Mars could be our second home? Mars lies on the outer edge of a habitable zone, a region of a solar system where liquid water on the surface may be supported if concentrated greenhouse gases could increase the atmospheric pressure. Almost all water on Mars today exists in the two permanent polar ice caps and planet crust. Mars was once a warmer, watery planet with much thicker atmosphere. Two of the major challenges in terraforming Mars are its thin atmosphere, which is about 0.6% of Earth atmosphere. In this atmosphere, our circulatory system will shut down in just 1 minute, and it have no global magnetic field, so it could not protect us from a solar wind. Terraforming Mars. So one of the major challenges of terraforming Mars is to increase its atmospheric pressure, which is currently 0.6 that of Earth. The Martian polar caps, minerals, and soil could provide the source of the carbon dioxide and water to thicken the atmosphere. Unfortunately, processing all sources available on Mars would only increase the pressure to about 7% that of Earth, far short what is needed. Only hope is that there is an accessible layer of calcium carbonate across the entire surface of Mars. We need about 10 kg of material per meter square to create Earth atmosphere for a 10 tons of CO2 per square meter on the surface. We need to dig down over a 10 meters across entire planet. But this is total assumption. So here is a time scale of creating a CO2 atmosphere. Cover Mars in solar, build 10 million gigawatt fusion power plant, robotic miners, processing plants, and pump water from the ice cap across the surface. But doing this all requires a lot of energy, and the atmosphere form will be not Earth-like. It will be toxic, and it will not host life. So we need to build an atmosphere which is not toxic. So we need non-toxic fillers like nitrogen. For that, we need to bombard comets and asteroids from Kepler's and asteroid belts, and also the comets and asteroids will bring water with them. And we need to introduce super greenhouse gases like CFC, because CO2 can't
Apparently, yeah, we're having some connectivity issues with Vikas. Oops, and oops, his connection, he stopped sharing. Vikas, are you able to continue? Issues with the Zoom meetings on online congresses. Vikas, are you there? Not sure if he can hear us. We can wait a few seconds to see if it works, or if not, we can carry on with the next one, and then we will come back to your presentation. I think it will be the best. Can you hear us, Vikas? Are you able to share your screen again, or can you hear us? He might not be able to.
Doesn't look like it.
No. Well, in that case, if you don't mind, we can actually proceed with the next one. Would that be okay? I guess so. Well, in that case, well, look, I think it's your turn.
Sure.
Yeah.
Okay, next up we have Grace Brock with the importance of microbial mutualists for the establishment of plants on Mars. This is actually a pre-recorded presentation, so Marco, if you'd like to roll the clip.
Yeah, Grace couldn't be with us today here today with us because she had another meeting, last minute meeting. So yeah. Okay. Seems to be the moment of connectivity for everyone. Is it working? Okay, go ahead whenever you want.
Hi everyone, my name is Grace and I'm a research assistant at Miami University in Oxford, Ohio, and today I'll be talking about the importance of microbial mutualists for the establishment of plants on Mars. So there's already been studies underway for several years to investigate how we can sustainably grow food away from Earth. So not only would succeeding in this teach us so much about how life can occur on other planets, but from a very practical standpoint, these studies are needed so that we can learn how to feed researchers on Mars that are participating in expeditions that may go on for years at a time. So we know we want to bring some supplies with us from Earth. It'll be very important to have our plants growing in Mars-based greenhouses, as this allows us to regulate temperature and light intensity, among many other things. And there's been many thorough, wonderful designs already for Martian greenhouses. But that's only part of the puzzle. We also need a medium for the plants to grow in, and hauling buckets of soil from Earth is fairly unsustainable. So because of this, I feel strongly that we should turn to microbial mutualists from Earth to help us amend the regolith that's already available in abundance on the surface of Mars. Luckily, from information gathered from Mars rovers, we believe that the regolith on site has the potential to support plant life after it's been rinsed to remove toxic components. So what's still limiting us, and how do we fix that? That's the big question. So first of all, the atmospheric nitrogen on Mars and on Earth actually is not readily available in a form for plant absorption. That's a very big problem. Also, nutrients potentially are going to be stuck in the rocky substrate of the regolith, and the dusty, fine composition itself of the regolith is lacking in structure, and this may lead to erosion and limited capacity to hold on to nutrients. So this is where microbes come in to help us out. On Earth, microbial mutualists have helped amend our barren soils and support plant life for many thousands of years. Two of the major microbial mutualists that we have are extremely hardy organisms that can be found all across the planet. Our Muscular mycorrhizal fungi are obligate symbionts of plants. They're microscopic organisms in the soil that aid in a plant's root absorption of nutrients such as nitrogen and phosphorus, as well as water. And they do this through very fine, far-reaching mycelial networks. These fungi are particularly suited to our needs on Mars because the mycelium harbor the potential to mobilize key nutrients that are stuck in that very rocky substrate of the regolith. Additionally, they're very, very good at producing soil aggregates, which would help stabilize the regolith, the outcome of which would not only support structurally the plant, but it would also increase the water capacity of the regolith and limit runoff of fertilizers. Likewise, rhizobial bacteria are essential because they're able to convert all of that atmospheric nitrogen on Mars into ammonia, making it accessible to plants. So it seems simple enough to send our Earth microbes into space and see what happens, but there's a bit of work that needs to be done first. Microbes and plants have very finicky recognition specificity, meaning some microbes aren't compatible with one another or their host plant. So thorough experimentation of compatible mutualist species must be done prior to sending any microbes into space. I propose the following experimental design as a means of pre-locally adapting microbial mutualists and desirable crop plant species to Martian greenhouse conditions prior to any future expeditions. So first, we'll collect soil samples from the rhizosphere of healthy plants from 5 sites. The sites being Topol Volcanic Zone on New Zealand's North Island, Mount Vesterhorn near the Vatnajökull ice cap in Iceland, the Michigan Sand Dunes, Mount Kilimanjaro's Alpine Deserts, and the Colorado Plateau. I chose these particular sites because their soil most closely resembles the composition of Martian regolith. They experience extreme environmental conditions or both of these things. So we would hope that the microbes here that we find in the soil from each site have adapted to allow the plant to do well in these extreme adverse conditions, and that makes them good candidates to aid in plant establishment on Mars. So with the soil from these sites, we will be creating trap cultures, which look like this. So we have the sterile soil in the pot first. We're putting site soil on top, so we can imagine this is soil from Colorado Plateau, and then we're capping that with more sterile soil just to make sure we don't get any cross-contamination. Next, we will choose 5 diverse crop species from a variety of plant families to determine which may thrive best under greenhouse conditions on Mars. So these are just 5 that I think make up a nice and diverse Martian diet. We could definitely play around with this. So I chose lettuce, sweet potato, soy, carrot, and corn. Our third step will be to set up a greenhouse experiment on Earth, of course, with each crop species sown into a trap culture pot, one for each site. We'll let these pots grow for 1 month and then test the plant roots, looking for evidence of fungi and bacterial colonization. And so by doing this, we'll get a colonization baseline because, again, we don't know exactly how host compatibility will play out. And from my own research experience, it's really a puzzle we just have to slowly work out over time. So here's an instance where soil from the same site minimally colonized Rudbeckia, but very heavily colonized sorghum, and the effects were very clear phenotypically as well. The sorghum plant looked much better than the Rudbeckia did. After obtaining our baseline of success, we'll then put the plants through a series of tests where we change one variable at a time that mimics the exact conditions of our Mars-based greenhouse. And our last variable to test is how these microbes and their host plants do in full regolith as their medium, because that's what's gonna be up there on Mars, of course. So instead of making trap cultures, we would extract the individual bacterial strains and the fungal spores from the site soil and inoculate that directly onto the roots of seedlings from each of our crop species. And I'll show a further demonstration in a moment of what this would look like, because I know it's a bit hard to visualize. And so by the end of this, we would hope to have isolated the top mutualists for each crop species that are capable of overcoming all of the environmental stressors of a Mars-based greenhouse. And very excitingly, we might also pinpoint mutualists that are capable of rapid evolution, which could prime them for unexpected challenges once on Mars. So this is the product design that I think would work very great for carrying out microbe inoculation on Mars. I recently attended a really interesting lecture given by Dr. Tobias Niederweiser, and I was very inspired by the fluid processing apparatus that Bioserve has come out with. So I would want to manipulate this device so that section A contains our plant seeds, which we would first eject out of the apparatus directly into the regolith. We'd wait a couple of weeks until the plant is a healthy seedling. Next, we would attach a pipette tip to the end of the apparatus and eject sections B and C, so our inocula, directly into the regolith around the plant's roots, thus inoculating them with the beneficial microbes. And finally, we would eject section D to give the plant a low dose of fertilizer to help ensure establishment. And lastly, I wanted to highlight the significance that this research could have for our continuing efforts to mitigate biodiversity loss here on Earth. This experiment, of course, offers very exciting potential for growing food on Mars, but additionally, the data we would obtain from a large-scale locally adapted mutualist experiment would help us as we try to recolonize ecologically damaged areas on Earth. So this is a picture of a North American prairie, and I'm currently participating in research where we've been studying the microbial mutualists that exist in, sadly, the few prairies that we have left, so that we can restore these incredibly important native areas of biodiversity here in the United States. And with that, I would like to thank the Astrobiology Society, the Congress, and my home lab with Jonathan Bauer at Miami University. Please feel free to contact me with any questions you may have, and I will reply right away. Thank you.
Yeah, well, look, it's yours. Well, anyway, thought I was just going to say that it was actually so nice, and it's a shame that Grace is not here with us today to ask some questions, because it will be an interesting discussion for sure. But we told her that if you have any questions, we will note them down, and we would forward them to her. So if you have any questions, you can, if you want to, either drop them in the chat or just tell them to us, and we will pass them on to her so she can get back to you with an answer. Any questions from anyone, or if not, I think Vikas is already here to carry on to the to finish his presentation. Well, if you have any questions, you can drop them down, and I will just forward them to her. So welcome again, Vikas. Are you ready to continue your presentation?
Yes, 1 minute, please.
Okay, yeah, sure. Glad to have you here. And yeah, okay. Whenever you're ready, just share your screen. Marcus, everything ready for him to share his screen? Well, yeah, I guess so. Okay, just making some time. you can either if you want to carry on from your work from where you were, that would be fine, or whatever you prefer. I think okay, that seems to start working. And that's just my face for now. Okay. Okay, that seems to be working. Are you going to carry on from the beginning or from where you were? How do you want to do it?
I want to restart from beginning.
Yeah, sure. I mean, yeah.
Okay. Good evening, everyone. Myself, Vikas Mishra. I'm a computer engineering student. I'm going to talk about space colonization, that is creating a permanent habitation and exploration of natural resources beyond Earth. But why we need to make life multiplanetary? Earth was subjected to 5 major mass extinction events, and a sixth mass extinction event is ongoing. Holocene extinction, a result of human activity driven by the population control and the overconsumption of natural resources. Many animals are becoming extinct due to this. The multiplanetary life is the solution to this, and Dawson's argument and will decrease the likelihood of our life extinction. If we make multiplanetary life, there may come a day when some plants and animals die out on Earth but are still alive on other planets. In another half billion years or so, the sun will expand and life will be impossible on the Earth. We need to establish a multiplanetary society by then, or mankind will be destroyed. Before we jump into space colonization, one of the most profound questions for the mankind: does life exist beyond Earth? And the hunt for this question and the hunt for this question and the human curiosity about space and alien life has led to the numerous discoveries about our universe. If life exists beyond Earth, then why we haven't found alien dead? Are we alone in whole universe? Is life on Earth the first but may not be the last? Are we looking in the wrong places? Could alien life be too far away from us that light may also have not reached us? Is our technology not capable to trace alien life? Could life be in the form of microbes and cosmic whites animal, and we may be only intelligent species in this universe? Maybe alien life failed to emerge quickly and enough to stabilize the planet and pave the foundation for the more life. As I said, our Earth was subjected to 5 major mass extinction events. Maybe alien life have not survived. Do they live beneath the ocean of a different worlds? Might be alien life be too advanced, a type 2 or type 3 civilization, and they don't bother about us? What if they are not a carbon-based life form? They may be a silicon-based life form, inorganic, or maybe robots. Who knows? Okay, can a 0.7 type civilization colonize planet? If yes, then how? Before we could jump on colonization mass, the rocky exoplanet found in habitable zone are likely for detecting liquid water on their surface, which may be the foundation for the life. So what is habitable zone or godlike zone? A habitable zone is the area around a star where it is not too hot, not too cold for a liquid water to exist on the surface of surrounding planets. We can colonize our space in 2 ways. First, terraformation or paraterraformation. Terraforming or terraformation is a process of modifying the atmosphere, temperature, surface topography, or ecology of a planet, moon, and other celestial body to and giving it a similar environment of Earth and making it a habitable. Next is paraterraformation, which is also known as a world house, which consists of creating a airtight bubble, many airtight bubbles in which we can live. Okay, if we want to colonize our universe and sail through the galaxy, we must start with our solar system. In our solar system, Mars and natural satellites Europa, Enceladus, Titan, Selicotus, Ganymede, Io, Triton, and Crane shows the possibility for hosting life and Europa and Enceladus show the highest possibility for supporting life. But why this show the possibility of hosting life? Titan. Titan atmosphere is considered similar to that of Earth, although somewhat thicker. The surface is characterized by the hydrocarbon lakes, cyclovolcanoes, methane, rain, and snow. Like Earth, Titan is shielded from the solar wind by its permanent planet for the most of its orbit, but the interaction with the moon's atmosphere remains sufficient to facilitate the creation of the complex organic molecules. It has a remote possibility of an exosuit methane-based biochemistry. Selicotus have a surface ocean heated by a tidal wave. Ganymede have a magnetic field with the ice subatom ocean stacked in a several layers with a salty water and has a second layer on the top of a rocky iron ore. Io. It is subjected to intense tidal heating, which make it the most volcanic active object in the atmosphere, and the outgassing generate a trace atmosphere. Titron may have a layer of a liquid water on a subsurface ocean. Dion may have an interior ocean, water ocean under the hundreds kilometers of a crust, possibly suitable for the microbe life. Kion may have an internal ocean of water and ammonia. Besides this, recently scientists found out the phosphine gas in Venus environment. The phosphine gas in Earth is released by industrial waste and by micro animals, which may indicate a sign of life on a Venus, a microbial life on Venus. Europa have a vast interior ocean beneath the surface maintained by the geological activity, tidal heating, and irradiation. The ocean water itself and even upper layer ice layer could be a potentially habitable. Enceladus have a subsurface liquid water ocean due to tidal heating or a geothermal activity. Free molecule has been detected, providing another potential energy source for a life. Also have vent on a floor of its subsurface ocean similar to Earth's when life was originated. We humans have just mapped 5% of Earth's ocean surface. So there may be a alien life on Earth beneath the oceans. So there is a possibility that these moons which have oceans can have a alien life. If we want to colonize the moons of Jupiter and Saturn and Neptune, we must first start with colonizing our Mars. But why red planet could be our second home? Red planet was once a warmer, watery planet with much thicker atmosphere. It lost its atmosphere due to its global magnetic field, which is too weak. Mars lies on the outer edge of a habitable zone, a region of a solar system where liquid water on surface may be supported if concentrated greenhouse gas could increase the atmospheric pressure. Almost all water on Mars today exists in polar ice caps and planet crust. What are the challenges in colonizing Mars? It have a reduced light level. It have a toxic and thin atmosphere. It have a toxic soil which consists of perchlorate salt, which is very sticky and toxic. There are global dust storms. There are no magnetic field to shield against solar wind. The average temperature is minus 63 degrees Celsius. Cosmic rays and UV radiation have a direct path to the Martian surface. Terraforming Mars, creating an Earth-like habitable environment on Mars. There are three major challenges for terraforming Mars. First, building up the atmosphere. Second, raising the temperature. Third, building a magnetosphere. So the atmospheric pressure of Mars is 0.6% that of Earth. That is one of the major challenges for terraforming Mars. If we want to thicken the environment of a Mars, we need to use its CO2, which consists of 95% of its atmosphere. The Martian polar caps, mineral and soil could provide the source of carbon dioxide and water to thicken the environment. Unfortunately, processing all sources available on Mars could only increase the pressure to about 7% that of Earth. So our only hope is our assumption that there is an accessible layer of calcium carbonate across the entire Martian surface. We need about 10,000 kg of Martian material per meter square to create an Earth-like atmosphere. For 10 tons of CO2 per square meter on the surface, we need to dig around 10 meters across the entire planet, which will require a lot of energy, several thousand times the total annual consumption energy of Earth. But if we succeed in utilizing its all CO2, and forming an atmosphere, the atmosphere form will be not Earth-like. It will be toxic and will not support life. So we need to build a non-toxic atmosphere, an Earth-like atmosphere. First, we need to introduce super greenhouse gases like CFC, because CO2 is not so good that it will increase greenhouse effect drastically. So we need non-toxic fillers like nitrogens. We need to introduce ammonia. To introduce nitrogen in Martian atmosphere, we need to bombard around 10,000 comets and asteroids into Mars.
Just one thing, also, because the time's kind of up, so try to wrap up as soon as possible. We'll carry on, but with that in mind, go ahead.
Okay. It will also bring a lot of water. So if we succeed in creating a Earth-like atmosphere filled with nitrogen, we can't let our atmosphere be leached. So we need to drop some bioengineered creature into Martian soil, which will release oxygen and will bring a photosynthesis on Martian surface. So our next and final step is protecting our environment from solar wind. That will be achieved by building an external magnetic field generator in front of planet that will have a same time period that of Mars, and which will deflect cosmic rays. Our next way is para-terraforming Mars, that is covering Martian land with many connected airtight bubbles. First, we need to create a semi-permanent outpost by shielding our habitat with a thick layer of ozone, CO2, which will protect us from cosmic rays and UV radiation. If we build our semi-permanent outpost near Martian polar caps, water will be easily available for our settlement. To grow anything, we must decontaminate soil and fertilize it. which will require a lot of energy and resources. For alternate, we can use an aquaponics to raise food. To overcome the low gravity, we need to set up centrifugal city and rotating habitat. Our exploration will be on Mars will be carried by robots and rover for mining Mars and setting our colony. If we want to explore further, we must build a moon base which will be act as our outpost for exploring cosmos. Installation of permanent outpost facility on the moon, enabling moon activity on the Mars. To meet our resource demand, we must do asteroid mining. To meet our energy demand, we must build a Dyson sphere, that is a mega structure that completely enclose a star and capture a large percentage of its power output, which will be achieved in following 5 ways: by getting energy, by mining mercury, by getting material into the orbit around the sun, and making a solar collector which will extract energy and we can use that energy. Using present day technology, we cannot colonize other worlds and find alien life. As civilization grow larger and become more advanced, its energy demands will increase rapidly due to its population growth and the energy requirement of its various machines. We need an alternate solution to Dosman argument, and we must overcome Holasian mass extinction and may require a human colonization of body other than Earth, such as Mars and the moons of different planets and other objects. Space colonization would facilitate the harvesting the solar system energy and material, and the possibility that the settlement on the other planet could decrease the likelihood of human extinction. Thank you.
Thank you so much, Vikas. That conveyed lots of ideas on a single presentation, which been very nice. If you can stop sharing your screen so we can carry on to the Q&A if anyone has any questions. Well, I don't know if anyone has any questions. I think there's one. Well, I actually have one. Yeah, any questions? Otherwise, I will ask mine, which is so. Do you think we have
Yes.
the right to colonize anything? I mean, obviously, we could do so at some point, but do we have the right to do so? I mean, because obviously, colonizing is not the same as exploring, which is a less invasive method. So, what do you think on this sense?
Carl Sagan once said that if there are Martians, whether they are microbes, we must not colonize Mars, and we must let that Mars for those microbes. So if there is an alien society, we must not disturb their environment, since we are destroying our environment. So destroying another life is not right. So if there is an alien life, we can have a cooperation with them, but colonizing other planet which have a alien life is not good. But if there is not a alien life, then yes, we can colonize that planet and celestial bodies.
Okay.
Hello?
Okay. Yeah. Okay. Makes sense. Yeah. Okay. Any other questions for him? Otherwise, we will carry on to the next one. Yeah, I think so. In that case, I think it's your turn to grab on. Well, next one is video, which was great. So, Alita, this is your turn, which is still my turn to keep talking. So, are you ready to present? Yeah. Hello.
Yes.
So, well, Alita Reggie is going to talk to us about asteroid mining. So, go ahead whenever you want. Okay, that's working. Yeah, we can see that. So, okay.
A very good evening to one and all. My name is Alita Reggie. I'm from the United Arab Emirates. I'm an aerospace engineer currently pursuing a master's in space. My topic for this evening is asteroid mining. This presentation will be done based on a case study on the target asteroid UW-158. This mission is designed with an attempt to study the surface composition of the asteroids and to flag potential mining zones for future missions. UW-158 was first spotted in 2011 by Pan-STARRS at the Halakela Observatory, revealing a stony asteroid with surface dimensions of approximately 300 × 600 meters. This asteroid also has a rotation period of 36 minutes. The asteroid was the talk of the scientific community for its presence of the rare earth metal platinum. Why go that far for platinum? The rise in prices of rare earth metals is expected to be a severe problem for the progress in technology in the coming years. Most computer chips, flat plates, green technologies use trace amounts of various scarce elements while Earth reserves are short. Platinum group metals are rare on Earth's crust as they're siderophiles, which mean they dissolve very easily into molten iron. Most metals of this family are trapped within the Earth's crust, leaving it inaccessible for us. Platinum and other rare earth elements such as gold, cobalt, iron, nickel, palladium, tungsten find their daily applications in our everyday lives, from medicine to automobile to space industry to every household. As platinum is one of the metals on this list, it is worth noting UW-158 seems like a good target as it follows an elliptical orbit, giving us profitable returns for the investment. The first mission to this asteroid would be a flyby exploration. The mission is designed such that the spacecraft depart from Earth with a true anomaly of 0 degree. The delta V, or the specific impulse required to perform the maneuver, is 1.855 kilometers per second. The spacecraft reaches Mars at a true anomaly of 180 degrees. Once at Mars's orbit, the spacecraft would then require to turn an angle of 58.47 degrees for gravity to put the spacecraft into UW-158's trajectory. The vehicle once would maintain a circular orbit of 4,000 meters above the surface of the asteroid to ensure safety of the spacecraft and deploy a rover with scientific instruments to study and collect samples from the surface of the asteroid. These figures in the slide depict the departure of the space shuttle from Earth, a hyperbolic trajectory, Earth to Mars trajectory, Mars to UW-158, and finally a Tizarine plot, which depicts the distance with respect to shuttle acceleration. Due to this asteroid's high-speed rotation as compared to other inner-belt asteroids, most effective means to study this asteroid would be to deploy a rover fitted with solar panels, sun sensors, telescopic cameras to capture high-resolution images of the asteroid, alpha particle X-ray spectrometer to study surface composition, along with 2 medium field of view descent cameras and a wide-angle color show camera to monitor collection equipment. The power and mass budget you see on this screen is determined based on the platinum that needs to be extracted. For this case study, the mine and extraction period is defined to be 20 days, assuming that on an average, the spacecraft operates in sunlight for half that period. This slide shows us an approximate calculation for a 20-day mining mission, giving us a profit of $2.85 billion in our current economy. Asteroids are an integral part of our study of the heavens due to the possibility of collisions with Earth. Though asteroid sites are rare, these trajectories are still studied due to the possibility that it helps us understand the origins of our solar system and their contributions to the building blocks of life. But recently, The supply of rare earth elements and volatiles have taken the scientific community by storm. These resources can be used for future human exploration, colonization in everyday competence on Earth, and to generate rocket fuel to explore and colonize further out into the solar system. Thank you.
Yeah, thank you so much, Alita. That was very interesting. Music very enjoyable, and it brought lots of interesting ideas, I think, on a very interesting topic, and that I'm pretty sure that it will be on trend for the next couple of years, especially now that we enter a next decade of space development and space exploration. I don't know if anyone has any questions. I think I don't know. Anyone wants? Okay, say Mike there. Yeah, go ahead.
Yeah, nice talk. Just have a question about the timescales. So what kind of technologies do you think are needed, and on what timescale will those technologies become available to be able to do this?
So I'm basically looking at a thermonuclear rocket. So as of now, this is not a very common practice. Another thing I forgot to mention was in my conclusion, I mentioned about volatiles. Most of these asteroids, along with rare earth elements, they contain volatiles such as water. So instead of carrying fuel from Earth, what we can do is harvest the water, use electrolysis, and generate power for the rockets. So the time frame for these would be, let's say, post 2030s, like post the first mission to Mars.
Okay, thank you.
Yeah, that seems pretty reasonable. Okay, say Ray there. Yeah.
Hi there, thanks, Lita. My question is about the costing, which flashed up very quickly on your screen. I don't need to see it again. It's just a question about the economics of this project, of this area, this endeavor. Were the figures that you quoted based on present day technology, or to what extent were the parameters in that calculation predicted rather than present day manifest elements,
Yeah, I get it. So for the present day scenario, what we assumed were the existing rocket technologies. So what we calculated was the mass of the rocket, including fuel, propellant, and total mass, and got the MD, which is the dry mass of the rocket. Then assumed for my rocket, the dry mass, I didn't show the calculation, but it was 4,200, something around the numbers. And for that, a Falcon 9 would be an ideal rocket, as a Falcon 9 has a 4,500 kg capacity for payload. So that was the rocket I chose. And all of these calculations are basically based on that. And yeah.
So is this a human mission? Would this require operators, or is this all automated? And is that technology with us now to do that?
Yeah, this is actually going to be a completely automated mission. So if you had actually noticed my last slide, I said one of the disadvantages would be that the low gravity. So human beings can't exactly be on the asteroid to drill. So the only way you can do is by having a harpoon from the rocket to the asteroid, and then you just send the rover in through that, land it on the asteroid, secure it through clamps. So basically it's going to be completely automated because the gravity is super low. You'll literally just fly off. So you can't have human missions.
That's great. Thanks.
Sure.
Yeah, that's been very, very, very great. I mean, congrats for such an amazing project. Yes, it's I'm pretty sure that we will be listening way more and more about this topic on the coming years. Thank you so much. And Luke, I think it's your turn to carry on.
Sure. So next up, we have another pre-recorded presentation. We have Gabriel Henrique Albuquerque Lins, who is also unable to be with us today. And his title is, How can the development of an integrated autologous exosuit help maintain the health integrity in space? So whenever you're ready, Marco, go for it.
Hello there,
Yep.
my name is Gabriel Lins, and this is my project. How can the development of integrated autologous exosuit helps maintain the health integrity on space?
Okay, sure, no problem. Well, it was working properly, so okay. Okay.
Hello there, my name is Gabriel Lins, and this is my project. How can the development of integrated autologous exosuit helps maintain the health integrity on space? The space isn't the best environment for humans. Just being there causes a lot of symptoms, like gastrointestinal and liver functions alterations, muscle and bones degeneration. It all starts with gravity. A different gravity from the Earth alters the force, the tension that the body is subject to, and consequently the flow of the metabolic events. The shift in microgravity causes a facial edema, the cranial veins dilate, and we have a head enlargement and other alterations. Because the blood is no longer being pulled to the extremities. For countermeasure that, the NASA used a lower body negative pressure device that mimics the original blood flow by suction. Of course, not the most comfortable solution, but talking about being comfortable, when we talk about spacesuits, that's the last word we hear about from astronauts. There is neck pain and fatigue and a lot of other small lesions. The actor suit being used in missions is focused at keeping the human side alive while he finishes what he needs. But remember that our objective is space exploration, and we don't think that's the really best path to follow. The spacesuit is nothing more than a really small spaceship focused at maintenance life. They have heaters on the gloves and boats, a radio for communication, and some sensors like electrocardiogram and another one for oxygen monitoring. And that's where we really start. I don't know why, but sensor isn't the first priority of the actual spacesuits. But remember about space exploration, they are indispensable, indispensable, and inexpensive. We can monitor, record, analyze a lot of important data like brain waves, skin state, muscle tensions, and others. I know that looks like the future, but we already have skin sensors that look like a tattoo that measure electrochemical alteration on skins. And if you think about Mars or moon bases, that's a really important information from glycolysis for diabetes to measure how much radiation someone took. There is this new trend on Internet of Things subject that's called Internet of Bodies, and it's about using the health data recorded from wearables to improve the user quality of life. And that is one of our goals. Imagining that you are outside the ship and something happens and you get scared. And the anxiety generated by that moment can put you at risk and make mistake. But however, if our sensors catch this anxiety peak and intervene with a therapy like biofeedback that you already had a train about that, you will quickly be fine again. Or we can use a laser therapy to decrease the pain or inflammation from an injury. And of course, for deeper conditions, we need more drastic interventions. And one of those options is to utilize one stimulator in neural pathways to cause modulation of systems such as balance, memory, location, and among others. For situations of metabolic control, such as pressure, loss of bone mass, and fighting infections, we need access to drugs that do not degrade in space. A solution to this problem is utilize nanomedicine, that we can modify them and adapt them even to new conditions that we discover as we explore space. And of course, we can let drug resistance happen, especially regarding cancer, which with all the radiation and host environment make it easier to happen. And nanomedicine, it's already taking care of this for us. But there is some alterations that are fast and muscle degradation are one of those. Without the gravity weight that rapid without the gravity weight, the muscles will rapidly atrophy, and the only actual countermeasure for that is doing a lot of exercise every day. That, in the long run, is not exactly the best of plans, and that's why we thought about using an exosuit by doing its function to the contrary. It will exert his force against the user, simulating the effect of gravity that, of course, would need to be adjusted according to environment or planet it is in, but we can leave artificial intelligence takes care of that. Using electromyograph sensors, we can have a good idea of how much tension is being exerted on the muscle. And with this information, we can know the correct amount of force to exert against it. And that is our concept, in which we unite all the ideas presented here in a light, comfortable, and inexpensive way. And that's our lab. And I'm glad to say that we are doing our best to make this project real. And that's our team. I would like to thank my supervisor, Professor Edgar Moria, my co-supervisors, Malia Câmara and Professor Julio Rezende, and of course, our amazing concept artist, Arthur Tavares. Thank you very much for listening to me, and goodbye.
Yeah. Okay. You have stopped sharing. Yeah. Again, this is a very well thought presentation, which is quite sad that Gabriel is not here with us today to ask some questions. But again, feel free to email us to astrobiologysoc@gmail.com if you want to send over any questions either to him or to any other of the presentations if you've reached this point of the Congress. And I'm sorry, Lucas, it was your turn, so feel free to carry on to the next one.
Sure. So the final presentation today is going to be Guibert Marquez Pascual with the title Valentina, A Journey into Space. Are you ready to go?
Yes, hi.
Hi.
I'm gonna share the screen. Let me see if just 1 minute. Can you see it?
Not yet.
Okay. Now?
Still nothing.
No? Wait. Okay.
Yeah, that's
now.
it. I can see it. Okay.
Now. So hi, my name is Guibert Marquez and I'm an undergraduate student of University in Alicante. And in this presentation, we're
One
going
second,
to
because
do...
am I the only one able to see just like your file?
Yeah, we can't see your
Explorer?
presentation.
We cannot see the proper presentation. We are just seeing like your file explorer.
Oh. Okay.
We do see that the presentation is stable. For some reason, no, it's not opening yet.
Okay, wait. I don't know.
I don't know, do you have a second screen or something like that that might be
I don't know why
preventing you from? So if you have it open and then click on the share screen button, you should be able to select just your presentation.
To try it like this.
Okay, now it's working. Yeah.
Even though I think I cannot put it any bigger, but sorry.
It's okay. Thanks for having that as a backup. Well, actually, I think that if you click not where it says page view at the left, where it says page view, it should enter the full mode screen. So if you want to try that.
Yeah, I'm trying, but it doesn't work. So I think
if
it's not a problem, I'm gonna leave it with like that.
It's totally fine. Thanks for having it as a backup.
Okay, so as I said, in this presentation, I'm going to talk about biosignatures. And here, I apologize for my graphic skills. This is a tardigrade, an extremophile organism that survives in extreme environments, such as deep sea hydrothermal vents, ice-covered lakes, and so on. And we are going to start a trip looking for the presence of life. Okay, so as I said, biosignatures are the signals which suggest unequivocally the presence of biological processes, and there are two kinds of different biosignatures. The ones that needs the presence of a scientist or a rover and are made physically in situ techniques. Regarding these techniques are the most efficient ones, but unfortunately we don't have the technology to go to other places and realize experiments, because as we know, the universe is very wide and big, and we are not able to do that. And remote methods are the techniques which for example, are in this image. We could see the G0 crater in Mars, and the spectrophotometer techniques are very useful in order to study the atmospheric species of a planet, and in order to establish that kind of science that could be a hint for the presence of life. Okay, and there are other features such as the morphology of a planet, the isotopic fractionations, the mineralogical evidence, the large enantiomeric excess, complex organics, and patterns in organic mixtures that could only be a hint in order to look for life, because life is something that has been debated for a long time ago, and it's not been established a proper definition, 100% proper definition. In fact, NASA has established the definition of life as a self-sustaining system, as we're going to see later on in this presentation. Okay, so moving forward, I want to remark that as we know, the probability of life existing on another world is as high as the probability of not finding it. Hence, we need to set a defining criteria to seek for life. And this is actually quite difficult for the reasons I've mentioned before. There is this base theorem that is based on a mathematical formula for determining the likelihood of an event based on a previous outcome occurring. Because life does not evolve or appear under just one condition. In fact, it is the sum of many events that led to the evolution of life. So as I was saying before, it's planning photometry, transmission, emission of light, and all that signals that arrive from us through telescopes are remote biosignatures and could give us a clue about whether this exoplanet it is or is not habitable. Okay, as I said, NASA has established a definition of life, And now is where we are in to the key point of this presentation. That is the criteria for life detection. As one companion said in another presentation, we cannot be 100% sure if life is only carbon-based, but most scientists accord that this is the most likely probability to happen, that life is carbon-based. So we can establish minimum requirements in order to build those devices that are going to go on the rovers on another exoplanets or planets such as Mars, the Perseverance, for example, and study and look for traits of life. Okay, the instrumental criteria must be that the device must be sensitive, contamination-free, because on Earth there are a lot of microorganisms that can be transported, such as tardigrades that live in very extreme conditions. So it is very important that we don't take there any molecule that could confuse us. So that would be called the false positive ones. As I said, the setting of defined criteria is very important, and there has been established a minimum traits that living beings have, such as molecular replication, cellularization, and metabolic networks. Every alive system has these same traits. Of course, depending on the environment, those could evolve in different ways, and perhaps could arrive to complex civilizations even. But how can we be sure we have found the presence of life? Well, as I said before, there are a lot of biosignatures that have been established because of biological processes that we know on Earth. The fact that we only know life on Earth limits us very much in terms of constructing those technologies that are going to be useful in order to find life. And the designs of those suitable devices for detection of replicatory systems processes should therefore be based on universal properties. There is a life detection chip made by the Center of Astrobiology of Spain that is able to recognize any organic molecule that could have been built in other planets, but that is not a trait of life, because as we know, many other organic molecules could have been found, and this is not a trait or indicates the presence of life. Many abiotic processes could develop in those organic signatures, organic biosignatures, sorry. But also another measurement target would be, or things that we have to look very deeper, because they are in such of a high importance, are the functional molecules, such as proteins, the biogenic organic polymers, and also polynucleic acids such as DNA and RNA. Because in order to a system to replicate, it needs to have a molecule that stores its information and goes through a metabolic pathways to be highly functional. This is an example of if we had found a fluid sample of another planet, how could we do it in order to see where is that? And that it's all. I finish with this sentence of Valentina Tereshkova, the first astronaut woman being in space. And it's "Hi, take off your hat, I'm on my way." And I think this represents the future of astrobiology. The many fields that are gathered together in order to go further in this science. I think it's very exciting, and it's just the first ways that we are seeing now. So that's all. Thank you so much.
Thanks very much. That was really interesting. Does anyone have any questions to ask?
I personally just wanted to say thank you, because it's been a very interesting journey, and no, it was interesting, a very interesting presentation, a great way of conveying lots of information. Thank you so much.
Ray?
Hi, Duet. That was great. A very clear exposition, a survey of the field, and you walked us through many what would otherwise have been really quite dense and complex measurements and processes. From the biochemical searches that have been conducted so far, where in our solar system do you think we are most likely to find something that can be detected using the technologies that you've described, that would be indicators, very promising indicators of life either having existed there at one time or existing at present?
It's such an interesting question, because, you know, life could have been in many planets in early or before, and we would have known about the existence of it. But I think that we have to look for the planets, the exoplanets that are in the habitable zone, the zone where it's not too hot, but it is under optimal conditions for the liquid water to be able to be there. So and also I think the dwarf stars that are the mainly stars that exist in our universe are quite good candidates in order to study in terms of the planets that are surrounding them.
That's fascinating. So you think there is more of a possibility of finding what it is that we're looking for outside of our solar system, exoplanets or better candidates? Is that right?
Well, actually, I think that in terms of practical opportunities, let's say that we cannot go further to that planet and realize in situ experiments. So what I'm trying to say is that I think in other systems there are high possibilities of life existing there. However, here in our solar system, we have more probabilities of finding life, if there it is, because we can go there and we can realize in situ experimental.
Okay, that's great. Thank you. That's very clear.
Thank you.
That's great. We have no other questions. I guess I'll hand over to Joaquin.
Well, yeah, just to wrap up in actually, because we've reached the end, so I think there's nothing else to say. We said lots of things at the beginning, and it's been a very quite interesting long afternoon. So thank you everyone for bearing with us, and thank you to all of our speakers for such nice presentations. I hope you have enjoyed being here with us as much as we have enjoyed having you with us today. And thank you also to our jury. And well, we look forward to hearing back from you. We will be in contact over the week. And thank you to everyone who's watching and who have supported us throughout this project, which is it's already been more than 2 months, one of our biggest ones. And also thank you to the rest of the committee for doing such nice work, as this has been a great thing, and I'm sure that all of our speakers have enjoyed having this opportunity. So hopefully see you in our award ceremony on the 6th of May, and that's it for today. Yeah, thank you everyone, and nice to see you all, and enjoy the rest of your day.
Thank you.
Bye everyone.
Bye.
Thanks everyone for coming.
Bye, thanks.